In this lecture, we are going to start the topic chemical bonding. It's actually one of the most important chapters. The reason being, you can do really well in chemical bonding. A lot of questions come and repeating pattern. Same examples on 3p varum. One of the easiest chapters where once you learn it well, you don't have to revise it. It will be very easy to do. Now, how we are going to see chemical bonding is, first we will go through the types of bonds, then we will go into Lewis dot structures. Using Lewis dot structures, we will develop into VSEP theory and then go on to valence bond theory and MO theory, molecular orbital theory. Okay. Each of them have their own advantages, own disadvantages. Okay. When you look into bonds, we know we have seen this before also. There are three types of bonds: ionic, covalent and metallic. Metallic bonds exist among metals, that is much easier to remember. Ionic bonds and covalent bond. Ionic bond is when the bonding between A and B becomes ionic if their electronegativity difference. Okay, I have given you the electronegativity values in periodicity lecture. The electronegativity difference is greater than roughly 1.7, 1.8. Okay, the more it is greater, the more ionic it is. Similarly, when you go to covalent, electronegativity difference is somewhere from 0 to 1.7. Okay. So, when you have something like 0 to 1.0, you call it non-polar covalent. When it is 1.0 to 1.7, this is polar covalent. Again, this particular number, for example, what do you take as 1.6? Is it covalent? Not completely. Is 2.0 ionic? Not completely. Okay, these are arbitrary values. Okay. Any ionic compound will have a certain degree of covalent character with it. Any covalent compound will have a certain degree of ionic character with it. Okay. In general, what can you say is, in ionic bond, one of the elements loses the electron to the other elements. For example, in our case, A could lose the electrons to B. A lost electron and has an octet. B gains electron and becomes an octet. Whereas here, neither A and B is strong enough to take the electrons completely. Okay, so what they do is they end up sharing the electrons so that both of them get an octet. Okay. Example would be here, NaCl, which comprises of Na plus and Cl minus. Example here is water. Okay. Now, the most important thing again you have to know is, when I say a compound is ionic, NaCl is not 100% ionic. Similarly, water is not 100% covalent. So, you can actually figure out how covalent a molecule is among a given set of molecules, or how ionic a molecule is among a given set of molecules. That will come in NEET. Okay, that's decided by Fajan's rule. Okay, now what Fajan's rule says is, you can see it either way. I am going to say it this way: percent covalent character in ionic molecules. Okay, I am going to figure out my percent covalent character in any of a given set of ionic molecules. I can give you 4 different ionic molecules in NEET exam, and I can actually do 2 types of question, or 3 types, which is the most ionic, which is the least ionic, or the order of their covalent character or ionic character. Okay, so I am going to figure out my percent covalent character in a given set of ionic molecule. Let us look into cation and anion. First, we want to look at this charge. Okay. For a molecule to be more and more covalent, percent covalent character goes up when the charge on the cation is high. Okay. Similarly, the charge on the anion is high. Okay. You can straight away remember it or think about it this way: I am ionic, I have a high charge, okay, high positive charge. What happens is, my Z effective has gone up right now. From periodicity we have seen Z effective has gone up. I want my electrons back. என்னோட greediness அதிகமாகும். என்கிட்ட இருந்து எலக்ட்ரானை வாங்க என்னோட greediness அதிகமானா, then I want it back. So what I will do is, instead of completely giving, okay, I will only give partially. So what it means, instead of completely giving is ionic, okay, not completely giving is covalent. So ரெண்டுத்துக்கு நடுவுல இருக்கும். So my percent ionic character decreases, percent covalent character increases. Charge அதிகமானா எனக்கு திருப்பி வேணும். Imagine my high negative charge. Okay, For example, we can take F minus O2 minus, ரெண்டுமே வந்து isoelectronic, but O2 minus has less proton to hold on to the 10 electrons. So because of that my Z effective is low, so என்னால என்னோட negative charge hold பண்ண முடியாது, so I cannot attract it completely, so I am not going to be completely ionic, some of it is taken back by my cation. So a high charge on either of the cation and anion is going to be useful to become a covalent character. Okay. Then size. When it comes to a cation, you want smaller size. When it comes to an anion, we want large size. Okay. Let's put it this way. Let's say this is a cation compared to another cation. Okay. So one of them is smaller in size. If you want, you can draw it this way. One of them is smaller in size, one of them is larger in size. There is an electron. Okay. Let's assume that is the electron these guys have given out. Okay. They have given out electron, but they want it back. Meaning ionica illama திருப்பி வந்து ஷேர் பண்ணிக்கலாம் சொல்லுது covalent. Who can attract the electron better? Obviously smaller size. So this can attract the electron better. This has a larger size, so the attraction is not that good. So you want a smaller size. Anion. Let's look at the anion. There is an electron here. This is a small anion. This is a large anion. Sorry. Now when you look at the valence electron that is being obtained from a cation, this is large in size, so this electron is far away from the nucleus, so this is not held tightly, whereas this is held tightly. If it is held tightly, I don't want to give it back, so I want to take it, I don't want to give it back, so I am ionic. இங்கே நான் வாங்கிட்டேன், ஆனால் என்னால் அதை வந்து ஹோல்ட் ஆன் பண்ண முடியல, ஸோ ஐ cannot really hold on. Any good cation will take it back away from me. So a large size of anion will give you your covalent character more. Then the next is polarization. Okay, polarization means how can I disturb the electron cloud in the another molecule. Okay, so I am a nucleus. How can I disturb the electron cloud in the other molecule and take the electron away from it? Okay, you want the polarizing power to be very high. Meaning I am a cation, I want to disturb the anion electron cloud very much, so I want that power to polarize it very much. Polarizing is just like poles, north pole, south pole, separate பண்றது electrons. So I want it to be very high. So when you look at from cation, okay, I am going to polarize it. So you talk about polarizing power for me. When you look at the anion side, a cation is polarizing me. Okay, so that property is called polarizability. Okay, the polarizability means the tendency to get polarized should be high. So again, I am easily polarized, I have a very high polarizing power. So all this set, okay, is going to be extremely useful. A lot of examples will come. One of a common example that comes in NEET is, for example, let's take sodium chloride, magnesium chloride, aluminum chloride. So this is plus 1, this is minus 1, this is plus 2, minus 1, so MgCl2, this is plus 3, minus 1, AlCl3. Okay, I can ask you which one is most covalent in this, or which one is most ionic, or arrange them in the order of covalency or ionic character. So when you look at it, the anion is similar, so I can ignore the anion. Cation is Na plus, Mg2 plus, Al3 plus. Okay, and they are in the same period. What I can do is I can look at charge. I want a very high charge, so this is the highest charge among them. Okay, so very high charge makes it most covalent. Your size of the cation should be small. In a given period, even without the cation formation, just a neutral atom, in a given period the size decreases because of Z effective. We have seen that. So just sodium, magnesium, aluminum size on the sodium is bigger than magnesium, which is bigger than aluminum. The more the charge you put, the size shrinks. So the smallest size. So when I take charge, this is how it is. When I take size, this is how it is. So I want the smallest size and the highest charge. So my AlCl3 in covalent character, AlCl3 is more covalent than MgCl2, more covalent than NaCl. Okay. Alright, now if you want, you can do one more example. We can look into Na2O, NaF. Okay, my sodium is same, but I am comparing my anions. I want the large size for a anion and a high charge. So this is really good in terms of charge. In terms of size, these are isoelectronic. Okay, both of them are 10 electrons held on by 8 protons, 9 protons. So obviously 8 protons cannot hold on to the 10 electrons very well, so size is bigger. So size also says. So Na2O is more covalent than NaF. This is how you can expect a question from Fajan's rule based on simple what is covalent, what is ionic. We will go into more detail of this later, solubility la use agum. Even here I want to make it a note. Fajan's rule, nobody will ask you the word Fajan's rule. You have to know a question is based on Fajan's rule. Either covalent character or ionic character, straight away. But the most important place where Fajan's rule is useful is when you are talking about solubility of salts. Solubility of a salt increases when ionic character increases. Solubility decreases when covalent character decreases. So any of this increases, this character, covalent character increases, solubility decreases. This will also come in salt analysis later. Okay, that's where this is going to be useful. Right. This is the first segment of chemical bonding. Next we'll go into actual chemical bonding itself. We are going to go into Lewis dot structures. Lewis dot structures by themselves will not come as a question, but they are the fundamental to build your VSEPA theory, and from there go on into shapes. They are extremely useful in writing organic mechanisms, okay, but basic structure also, Lewis dot structure is going to be useful. First thing you want to know is Lewis dot structure is not going to give you shape. Okay, we will use the structures to get the shapes later, but this will not give you shape. This will tell you a simple electronic arrangement when a molecule is given. Okay, couple of rules are there, and there are a couple of ways you can draw Lewis dot structure. No particular way. We will deal with the simplest way possible. Okay, what you want to do is, once you are given a molecule, you want to put the central atom and put the other atoms around it. No need to worry about shape or angle, just put them around it. Okay, so let's say for example, we'll go with the simpler one, CH4. Okay, so there are 4 hydrogens, so I'm just going to put simply around it. Okay, first thing you want to calculate is the number of valence electron, total valence electron in all of these elements. Carbon has 4 valence electron plus each hydrogen has 1 valence electron, so that takes total of 8 valence electrons. Alright, now we have calculated the valence electrons. So again, now calculate number of valence electron. Step 2, connect the atoms with single covalent bond. So I am just going to do this. Okay, they have to be held together, otherwise they won't stick together. Okay, so I have done this. Now each bond is 2 electrons. The next step is count the bond pair electrons. Okay, in our case each bond is 2 electrons, bond pair, a pair of electrons, 2 electrons form a bond, 1 2 3 4, so that is 8 electrons in this case. Okay, 8 electrons. Now count unaccounted electrons. Okay, in this case 8 valence electron, 8 electrons are shown in bonding, so no valence electrons possible. So this is going to be the Lewis dot structure of CH4. Okay, simple, straightforward. Now this is going to be good enough for CH4. Now we will go into something which doesn't finish off right here. For example, water, H2O. I have 2 plus 6, okay, 8 electrons. I know my oxygen is the central atom. I connect my hydrogens through a single bond. Now what do you want to do? This step number 5 will change depending on the atom. Okay, mostly you want the unaccounted electrons to be assigned as lone pairs to the most electronegative element or the terminal element. That will be case by case basis. Most of the time the terminal element, okay, will be the most electronegative. In our case we don't. Okay, couple of points you want to know. Fluorine and hydrogen are always terminal elements. Okay, only one bond now possible, so they are always going to be terminal elements. Oxygen can be terminal or non-terminal, but what you want to do, you want to assign lone pairs to most electronegative or terminal atoms, okay, till they get octet. Okay. Now the next step is, I have assigned all the extra electrons, I have assigned most of them for the terminal or electronegative atom till they got octet. Then what do? The remaining electrons I assign to elements that are atoms I missed here. இப்போ terminal மட்டும் போட்டிருக்கீங்கன்னா central atomல போகும். Assign remaining electrons to rest of the atoms. And the last step, okay, now I have done all this. What can happen is, because I assigned the electrons to terminal atom or the electronegative atom till they got the octet, okay, they are okay, but the rest of the atom, most of the time the central atom doesn't have to have an octet. மிச்சம் இருக்கிற electron, total electronல நான் வந்து bond pair போக மிச்சம் இருக்கிற electron count பண்ணியாச்சு. அந்த electron வந்து நான் lone pair terminal atomsக்கு போட்டாச்சு. அப்ப central atomக்கு electron மிச்சம் இருக்கலாம் இல்ல இல்லாம இருக்கலாம், octet இல்லாம இருக்கலாம். So what you want to do last is share lone pair electrons with central atom. Okay, now we will see it as an example. Now I have 8 electrons. I have done the basic bonds. I have counted the bond pair electrons. 2 plus 2 4, total is 8. Okay, so out of 8 I have 4 accounted for, remaining 4 I have to do. Hydrogen you never worry because it already has an octet. Hydrogen octet nu solla mudiyadhu, fully filled shell, 2 electron vandiruchu idhula. So I have 8 electrons. 2 plus 2 4 is accounted. So remaining 4 I have to assign to the most electronegative atom. Now when you see oxygen, it has 1 2 3 4 5 6 7 8 octet. So oxygen is good. Let's go for an example that is a little different. Let's go to CO2. Carbon is the central atom, bonded to one oxygen on one side, the other oxygen on the other side with a single bond. Now when you look at the electrons, carbon has 4 electrons, oxygen has 6 electrons, so that's 12, 13, 14, 15, 16 electrons. Okay, 2 plus 2, 4 electrons is counted for bond pair. So total is 16, 4 is counted, the remaining I have to do 12 electrons. I assign it to the most electronegative element, oxygen. So 12 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so again 4 plus 6 times 2 is 12 is 16 electrons. Out of 16 I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So everything is good. Now I don't have any more remaining electrons to assign to the rest of the atom. Now when you look at octet, oxygen has an octet. Okay. See, oxygen has an octet. This oxygen has an octet. But the carbon doesn't have an octet, it has only 4 electrons. So what do we do? Share the lone pair electrons with central atom. So I am going to be sharing this electron. So if I share this electron, this oxygen is not going to lose the octet. Okay, if I have 2 electrons, I am sharing it with you, I am not losing them. So my octet is not going to be gone. So if I do this, carbon has 2 plus 2, 4, 5, 6, not enough. So 2 more. So now what we have is oxygen, This becomes a double bond carbon, double bond oxygen. Okay, 2 lone pairs are still there. 2 lone pairs are still there. This will be the Lewis dot diagram of CO2. Again, I am not looking into shape or hybridization, just the Lewis dot diagram. Okay, all right. We will do one more that's a little different than these, where there are competing Lewis dot structures. Okay, CO, it's a very good example because it also comes later in your coordination chemistry. It's a ligand. So this has 4 electrons, valence electrons. Okay, and oxygen has 6 electrons, valence electrons. So that is comprising a total of 10 electrons. Carbon, single bond, oxygen. Okay, that is 2 electrons accounted for. Okay, 2 is accounted, there is 10. So I have to account for 8. 1, 2, 3, 4, 5, 6, 7, 8. Alright. So now when you look at octet, this is octet, 8 electrons, 2, 4, 6, 7, 8. This has only 2 plus 2, 4 electrons for carbon. Not enough. So I want to make multiple bonds. In the bond you move panna, share apping 4 electrons. That tells me one thing. This electron has to be moved. When I move that electron, I end up with carbon, double bond oxygen. I have this. Now when you see my oxygen, 2, 4, 5, 6, 7, 8, 8 valence electron or 8 electrons, octet is okay. Whereas my carbon, when you see 2, 4, 5, 6, 6 electron, not enough. So I have to move these 2 electrons as well. So there is pair of electrons here, pair of electrons here. Okay. Now when you look at it, oxygen has an octet, carbon also has an octet. So this is the Lewis dot structure of CO. Now when you look at CO, there is a lot of things that you need to know. Carbon came with 4 electrons. Okay. 1, 2, it has given 1 electron for this bond, 1 electron for this bond. For this bond, it has not contributed even a single electron. Both electrons come from oxygen. So what you do is, okay, this is a normal electron where carbon has 1 from here, 1 from here, but here it has not donated, it is all oxygen's electron. So what you can do is, to show these type of bonds, you show it this way. An arrow with a positive tail, meaning this element has lost the electrons, this is gaining electrons, not completely, not ionic. Sharing layer, it's not mutual sharing. I am just borrowing yours. It still belongs to you and the electron is always yours, but I am sharing it. This is called coordinate covalent bond. Okay. It always faces the element that is receiving the electrons, and the positive tail shows who has lost the electrons. And this is the CO structure. Now when you see it as a ligand, the carbon can donate or oxygen can donate. The carbon is the lower electronegative element. So when it behaves as a ligand, later you will see in coordination chemistry, it's a carbon donor, hence it's a very strong ligand. Okay. Last example that I want to do, it's a recurring example in NEET. It has come many times. Not only the particular example, also its corresponding species. NO2. Nitrogen has 5 valence electron plus oxygen has 6 valence electron. Okay. So that is comprises a total of 7 valence electron. Nitrogen, oxygen, oxygen. So now I have shown 2 plus 2, 4 electrons. Out of 17, 4 is shown. Okay, remaining 13 electrons I have to show. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 electrons. Again, I have assigned everything for the terminal atom. Remaining electron are assigned for the central atom. This is an odd electron molecule. So there is no way you will get a lone pair here. You will have only 1 electron right here. Okay. Now, when you look at it, this oxygen has 8 electrons, this oxygen has 8 electrons, but nitrogen has 2 plus 2, 4 plus 1, 5. So it wants 2 more. So this oxygen can give. So I will have nitrogen, double bond oxygen, oxygen, okay. Now when you see this oxygen, it has 8 electrons. This oxygen has 8 electrons. The nitrogen has 7 electrons. Okay.